Okay, good Friday evening to everybody, and welcome to another online review session in organic chemistry. In today's session, we are going to review for the third exam, that is exam number 3, that is scheduled for Tuesday, April 8th. And for this review session, we are going to use the Spring 2013 exam number 3. Some of the questions in this exam we have done before, so I will be doing those questions that have not been covered in class from this particular exam. Okay, and as we go along during the session, I will acknowledge those of you who have joined us. So far, I see Alexis Oyetubo, Frederick Todd, Mashake Hutchinson, Victoria Larson. Okay, so to get the session started, let us go to what I want to do. I will start with question number 4, which is a fairly simple question, just as an icebreaker. And then from question number 4, I will go to questions 7, then from 7 to 8, then from 8 to 10, then 13, 14, and 15. Okay, so to get the session started, let me call upon Mashake. Can you go ahead and read this question for us?
Fill in the missing reagents.
Okay, thank you. But before you drop the mic, let me ask you a couple of questions. Do you have an idea what the reagent for this transformation is going to be? In other words, going from an alkene to a primary alcohol. Any idea what the reagent will be?
Borane.
Okay, very good. Borane. Okay. Step 1.
And step 2, hydrogen peroxide in the presence of hydroxide ions.
Okay, excellent, excellent. Okay, step 2, hydrogen peroxide in the presence of hydroxide ion. Great. So what this reagent does, this combination here, step 1 and step 2, is to convert a carbon-carbon double bond to a primary, in this case, to an alcohol. In other words, we are going to add element of water across this carbon-carbon double bond, and this is we call an anti-Markovnikov addition of water, and that is what this reagent will do. By anti-Markovnikov of water across the carbon-carbon double bond, what we mean by that, the hydrogen goes to the carbon that contains less hydrogen, and the OH group goes to the carbon that contains more hydrogen. And that is what you have here. Okay, this carbon is this carbon right here. And this carbon here is this carbon. So what we've done now, we have added water across the carbon-carbon double bond. And that is what this reagent does. Okay? Now, let us go to the next one, B. Okay, anybody has an idea what we need for B, going from a primary alcohol to an alkyl bromide? Anybody has an idea? Either pick up the mic or you send me your answer through the chat window. Excellent. Phosphorus tribromide. Okay, excellent. That is correct. In other words, in order to transform, in this case, a primary alcohol or sometimes a secondary alcohol to an alkyl bromide, what you need this reagent here. Phosphorus tribromide. Okay, very good. Now the next one, we want to go from this alkyl bromide here. We now want to replace the bromine with a cyanide right here. Okay, we want to replace the bromine with a cyanide. Okay, so therefore, what do we need to do this? Okay, what reagent do we need to do that? Okay, sodium cyanide, excellent. Sodium cyanide. You could also use, in this case, you could also use potassium cyanide. And this is an SN2 reaction. This is an SN2 reaction. Okay, by SN2 reaction, we mean that the substrate, in other words, the starting material that contains the leaving group, that leaving group must be attached to either a primary carbon or sometimes a secondary carbon. Also, it could be attached to a methyl carbon. For example, this here, this will also undergo similar reaction with a cyanide to give you this here. Because in this case, the leaving group is attached to a methyl group. So keep in mind, anytime you are dealing with an SN2 reaction, in this case, you have a nucleophile, which is the cyanide, and it will be attacking this carbon here, and then this group will be leaving. That leaving group must be attached to a primary carbon, sometime a secondary carbon, and sometime a methyl carbon. Okay, very good. So now we've done this. So what this has shown us here is one of those methods for making nitriles. This is one of the methods for making nitriles. Okay, SN2 reaction with an alkyl, bromide, or sometimes chloride, or sometimes iodide. Okay, about B. About D, sorry about that. About D, you want to go from a cyanide to a nitrile to a carboxylic acid. Okay, very good. Okay, so what this is simply showing us is giving us a method for the synthesis of carboxylic acid. So all of you said hydronium ion. That is correct. Excellent, excellent, excellent. Okay, so here we use hydronium ion. And sometimes you could also, if you want to hydrolyze a nitrite to carboxylic acid, sometimes you could use basic hydrolysis. In other words, you could do this. You could use hydrolysis under basic condition. Use hydroxide in water, of course. In this case, you have to say step 1, and then you say step 2 to protonate the resulting carboxylate. And that, in that case, you get this here, okay? And you do this sometimes when you have a sensitive group in the molecule. For example, if you have this molecule here, and you want to hydrolyze this with carboxylic acid, in this case, the best reagent to use is do the hydrolysis under basic condition, because if you do not do that, you will be dehydrating this hydroxy group right here. You don't want to do that. So therefore, under this condition here, this will be the best reagent. Step 1 and then step 2. Okay? Because if you just start off by doing this here, what you are going to get will be this here. Okay, you get an alkane. Okay, so keep that in mind. Okay, now, so now about going from this carboxylic acid to a primary alcohol. What reagent do we need here? Okay, LAH, exactly. Followed by LAH, followed by, Okay, very good. Okay, lithium aluminum hydride, which is LaH, and then we follow that always hydronium ion. Okay, very good. So we are moving right along. What this reagent will do, anytime you have a carboxyl group, okay, this reagent will transform that carboxyl group to a primary alcohol. It does not matter where that carboxyl group is, okay? What it does is simply take the carboxyl group, regardless of whatever is in the rest of the molecule, take the carboxyl group to a primary alcohol. You could also use, in this instance here, you could also use this reagent. We could also use this, I would say, or step 1, you could use borane followed by hydrogen peroxide under basic condition. Okay, so both of these reagents you could use to transform a carboxylic acid to a primary alcohol. Okay, about the last step here, F. What do we need here? We want to go from a primary alcohol to an aldehyde. This is an aldehyde. Okay, PCC. Okay, PCC, very good, excellent. PCC. Okay, let us see here. So you say PCC. What other reagent can we use? What other reagent can we use? Okay, yes, we could also use, excellent, we could also use desmartin, iodine. Okay, so if you guys just say desmartin, that is fine. Okay, so what these reagents will do, both of these reagents, what they do is to take a primary alcohol and transform a primary alcohol to an aldehyde. Also, they could also take, these two reagents will also take a secondary alcohol and oxidize a secondary alcohol to a ketone. Okay, so you need to know that also. For example, you could have this, that these two reagents here could also take a secondary alcohol, PCC, or desmartin to a ketone. Okay? Now, if all of this is clear to you, give me a happy face. Okay, very good. I also notice here that Danuchika Gelin has joined us. You are welcome. Okay, so let us now go to question number 7. Okay, Victoria, can you go ahead and read question 7 for us?
Starting with cyclobutanone and using appropriate reactions, including the Favorsky reaction, provide a synthetic scheme for cyclobutane carboxylic acid.
Okay, thank you very much. But before you go, let me ask you a question here. We are supposed to start with cyclobutanone. Okay, how many carbon atoms do we have in this cyclobutanone? How many carbon atoms?
4.
4, excellent. Okay, very good. Okay, so therefore we are told to start with this. Okay, and then they told us that we need to use the Favorsky reaction, and then to give this product here. Apparently we have to use several steps. Cyclobutane carboxylic acid. Okay, which is this here? Okay, I also see that Chad Crawford has joined us. Chad, you are welcome. Okay, so that is what we want to do here. Now, they told us we have to use the Favorsky reaction. Now you know that if we have to use Favorsky reaction and we have to make this product here, does anybody have an idea where this product will come from if we use Przewalski reaction? How many carbon atoms will be in that starting material? Okay, cyclopentanol. Okay, yes. Okay, thank you. Victoria says we need to start with cyclopentanol. Excellent. That is correct. So therefore, once you recognize that, because you know that you have to do Przewalski reaction, you need to go here, from here to here, and then the next question that comes to your mind is, okay, if we are supposed to make this, and we know that we have to start with this here, cyclobutanol, which only contains 4 carbon atoms, somehow we have to go from here to here, which means that we need to do ring expansion. Okay, and once we do the ring expansion, then we have to do ring contraction, which is our Przewalski reaction. Okay, now how do we do this? I believe we only have one reagent that will allow us, that you guys know of, that will allow us to do a ring expansion. So let us look at the synthetic scheme. Anybody has an idea? We have to start from here. Okay, diazomethane. Excellent, excellent. That is the only reagent that we know that will give us ring expansion. So therefore, you take this, then you take diazomethane, very simple reagent. Okay, once you take diazomethane, what that gives you, it gives you a ring expansion. That ketone is expanded by 1 carbon atom to form another ketone, plus of course you are going to also spit out or produce nitrogen in this particular instance here. Okay, so now we form our cyclopentanone. Okay, so this is one step of the synthetic scheme. Now what do we need to do now? What reagent do we now need to do to go to here? Anybody has an idea? Okay. Okay, excellent, excellent, great, great, great. Okay, that is correct. Okay, but before you, okay, so you do hydroxide with, okay, excellent. Okay, very good, excellent. So now you take this cyclopentanone. What we now want to do is to brominate, do an alpha bromination. Okay, you could do hydroxide in base, or you could also use acetic acid. Also in, hydroxide with bromine, or acetic acid with bromine. Each one of these reagents will allow us to brominate the alpha hydrogen, that is the carbon, that the hydrogen attached to the carbon, which is attached to a carbonyl group. Okay, so now we have this here. So now we have the alpha bromo compound, alpha bromo cyclohexanone. Now what do we need from here? Once we do this, then what do we need to do? Anybody has an idea? Okay. Okay, good. Okay, so now you do this. Step 1, you do the hydroxide first. Of course, this is in water. And then step 2, you do the hydronium ion, okay, in order to protonate the resulting carboxylate. Okay, so what this reagent does, anytime you have an alpha bromo or alpha halo, In other words, it could be chlorine or it could be iodine. Okay, so if you have an alpha halo ketone, cyclic ketone, and then you take this combination of reagent, hydroxide followed by hydronium ion, what you do now is to do a ring contraction. In other words, you are now going to form, instead of a 5-member ring, you are going to form a 4-member ring, in this case, plus a carboxylic acid. Okay? For example, if you have this, okay, if you have this, you have this here, and then you do that same reaction, step 1, and then you say step 2. Okay, then you get this here. So now you go from a 6-member ring to a 5-member ring. Okay? Now if you follow that, give me a happy face. In other words, the synthetic scheme that they are asking for in this case is this here, going from here to here, of course to here. Okay, this is our synthetic scheme right here. Okay, going from this cyclobutanol, reacting with diazomethane, then getting the cyclopentanone, and then you then do the alpha bromination of the cyclopentanone, and then you react the alpha bromo cyclopentanone with base followed by protonation to get the cyclobutane carboxylic acid. Okay, very good. Okay, by the way, let me see here. Okay. Okay, let us go to the next question. Okay, that would be question number 8. Okay, let's see here. Frederick, can you go ahead and read this question for us?
Starting with malonic ester and other appropriate reactions, write a synthetic scheme for cyclopentane carbonitrile acid.
Oh, okay. Actually, it should be carbonitride. Yes, this is a mistake right here. It should be just carbonitride, not carbonitrile acid. Thank you. Okay, now let us see what do we need to do here. So what they want us to do is to take malonic ester, and then they want us to make cyclopentane carbonitrile. So you need to know what the structure of this compound is. In other words, they are also testing your knowledge of nomenclature. Okay, so that is cyclopentane carbonitrile. Okay, so let us do a little bit of analysis here. If you take this molecule here, okay, you have to make an assumption that the carbon of the carbon-nitrogen triple bond will be coming from this carbon here. You have to make an assumption that it will be coming from either this carboxyl carbon here or this carboxyl carbon here. Okay, when you do, after you finish your malonic ester synthesis. You also have to assume that after the malonic ester synthesis, the carboxylic acid that you obtain will have to be converted to a nitrile, okay? So you need to keep that in mind. Now, once you have that in mind, then you also have to make an assumption that this alpha carbon here must be this carbon, okay? If that is the case, what this is telling us is that we need to join 2 carbon atoms to this alpha carbon here. Okay, so there is a carbon here. We join this here. We have to join this here. We also have to join this here. So we have to do 2 alkylation. In other words, we have to do 2 alkylation. And one of those will have to be a regular alkylation, and the second alkylation will have to be an intramolecular alkylation. Intramolecular. And then you then tell yourself that, okay, what kind of alkyl group, bromide or chloride do I need to use? Okay, say, okay, so if this is the alpha carbon, and you are joining to this, and joining to this, therefore you need 1, 2, 3, and 4. So you need 4 carbon in that alkylating agent. Okay, so let us start here. We are going to start with malonic ester or ethyl malonate. Okay, the question I have for you is, what is the first thing we do now? What is the first thing that we need to do? What is the first thing that we need to do? Okay, form the enolate. Excellent. So the first thing you need to do is form the enolate. In this case, since we have the ethoxide as part of this, an ethyl group in the ester functionality, so we want to use an ethoxide here to form the enolate. And once we do that, you get this here. Well, I tell you what, we don't need to go through. Let us simply say 1 to save ourselves some time. We say step 1. So this step 1 form the enolate. Then step 2, then you add your alkylating agent. So that alkylating agent must be such that you have a dialkyl bromide or a diiodobromide, because you want to be able to alkylate at the first alkylation, and then the second alkylation will have to be an intramolecular reaction. So you have this here. So how many carbon do we have here? 1, 2, 3, and 4. So we have 4 carbons here. Okay, so what do we get here? We get this. So in our first alkylation, we get that. Okay, we now join this here. Okay, that is 1, 2, 3, 4. So we have 4 carbons here. And then what is the next thing that we do now? Can anybody tell us what is the next thing that we do? Another alkylation, another enolate formation. Excellent. Okay, step 1 again. Well, in this particular instance, we already have this here, so we don't even need to say step 1 because we already have this in here. It's part of the molecule. So once you form your enolate here, that enolate will simply now come in, attack this carbon here in an SN2 reaction. Keep in mind, this is an SN2 reaction. So at this point, you are going to now form your cyclic molecule. Now, this will now be here. Got the green pen, yes. Okay, that is 1, 2, 3, and 4. So now we form our 5-member ring molecule. Now, what is the next step that we need to do now? Keep in mind, ultimately, this is where we want to come to. Okay, yes. You now want to do hydrolysis. Very good. You now want to do hydrolysis. Take this out. Okay, so once you do your hydrolysis, you want to transform this ester functionality to carboxylic group. So now you have this. Okay, and then once you have that, then what do you do next? What do you do next? Oh, heat. Okay, very good. You're now going to apply heat. Okay, so now we say we apply heat. And that will give us the monocarboxy compound, monocarboxylic acid. We use it. Let us be consistent here. Use a green pen. Plus you now have your, and one of these hydrogen now will be here. Okay, because once you lose your carbon dioxide here, once you apply the heat, you lose carbon dioxide here, and this hydrogen here simply comes to here once your enolate ion is formed right here. Okay, so now plus carbon dioxide. Now, what do we need to do now? Keep in mind, this is what we want to come. Okay, what do we need to do now? DCC and ammonia. Okay, very good. DCC and ammonia. So at this point, I am assuming you guys want to form the primary amide. Okay, now once you form the primary amide, what is the next step from here? Okay, now you do dehydration using thionyl chloride. Okay, what happens? Thionyl chloride will take a primary amide and form a nitrile. So this is another method for the synthesis of nitrile. Okay, so now we are finally, and this is this product here, and that is the product they want us to make. This here is this right here. Now, if you follow that, give me a happy face. Okay, excellent. Okay, so now let us go to question number 10. Okay, folks, those of you who came in a little late, I am going through most of the questions that we did not go through in class because the rest of the exam 3 of spring 2013, I believe we have gone through most of those in class already. Okay, now number 10. Let's see here. Okay, I believe Freddie. Okay, let me go. If I have not spoken to you tonight and you have not read a question for us, and your mic is working, can you pick up the mic and read this question for us?
Starting with butanolic acid and any appropriate reagents and reactions, provide a synthetic scheme for 2-hexanone.
Okay, thank you. I believe that was Alexis. Okay, very good. Okay, so now you have this. We are supposed to start with butanolic acid, okay, and any appropriate reagents, and then to make 2-hexanone. So in other words, we go from here to here. We want to make a 2-hexanone. So we are also testing your knowledge of nomenclature here. Okay, so what are we doing here? Let me ask you, we are going from a 4-carbon starting material, to a 6-carbon starting material. Okay, we are going from a 4-carbon starting material to a 6-carbon a 6-carbon product. Okay, so let me number this. This is 1, this is 2, this is 3, and this is 4. Okay, let us start numbering from here. Let's say this is 1, this is 2, this is 3, 4, 5, and 6. Okay. We need to, so how many carbon atoms? Oh, by the way, where are we going to join this? The new carbon. We need to form new carbon-carbon bond. Okay, where do you think we need to join this new carbon-carbon bond? Keeping in mind that we will have a number 1 here. Okay, and then number 2, number 3. Where do you think we need to join this new carbon-carbon bond? Using the starting material. No, using the starting material, where do we need to join the new carbon-carbon bond? Okay. Okay, that has to be carbon number 1. Right, very good. Okay, very good. Excellent. Very excellent. Carbon number 1. So therefore, we need to join a carbon to this carbon number 1. So if we have to do that, then you ask yourself, how many ways do we need to, do you know of making new carbon-carbon bond? Of course, starting with carboxylic acid. So that is the question that you almost have to answer. So how do we do this? Let us start. Let us start. So I need your help here. So for this synthetic scheme, how do we start this? Keeping in mind that you need to form new carbon-carbon bond. Okay, so what do we do with this? What do we do with the starting material? Keeping in mind, okay, you want to form LAH. Okay, very good. Very good, okay. I'm assuming that you want to do LAH. Okay, LAH followed by, and of course you all know that LAH reacting with carboxylic acid will give you a primary alcohol. Now, what other reagent can you use for this? What other reagent can you use for this? Okay, borane, exactly. Borane followed by hydrogen peroxide. Okay. Okay, so now once you form this, then what do you do with this, with the primary alcohol? What do you do with the primary? Okay, you now want to react with PbR3. Okay, and that will replace the bromine will replace the hydroxy group here. Okay, very good. Okay, I'm assuming that you are setting this up for the formation of a new carbon-carbon bond. Okay, now what do we do from here? Now what do we do? Okay, you want to form a Grignard. Okay, very good. You want to form a Grignard. I wasn't really thinking Grignard, but that could be a good one. But there are so many ways in which you could approach some of these problems. So your own ingenuity is the only limitation here. So that's why I keep telling you, we want to encourage you to think critically. So I wasn't thinking about this, but I think this might work. Now, what do you want to do with that? Okay, what do we do after that? We form your Grignard reagent. Okay, you now want to dump in an aldehyde. Excellent. Okay, I am assuming here that you want to start with this here, this aldehyde. Let us change the color. And then you follow that up with hydronium ion. So therefore, you are going to form this. So keep in mind, a Grignard reagent will react with an aldehyde to form a secondary alcohol. So you need to know that. So apparently, I believe who gave us that, that was Marsha. So you must know that that is what we are going to get. So now you have this. Okay, so this green here will react with an aldehyde to give us a secondary alcohol. So now what do you want to do with that? Now do PCC. Very good. Excellent. Excellent. PCC. Okay? Or you could also use des-Martin iodine. Okay? Okay, so now and that will give us this here. Okay, very good. Okay, so that will work. What I was really thinking, I was also thinking that you could have used, oh, by the way, that is an excellent one. Marsha, that was very good. I was also thinking that you could use, at this point, an SN2 reaction, sodium cyanide. Use the SN2 reaction here. Okay, and with that you get this here. Okay, and now once you get that, you could now react this with a Grignard reagent. That was really what I was thinking. You could now react this with a Grignard reagent, but this is just as good. This is just as good. Okay, so here you then take your Grignard reagent. Step 1, take a methyl Grignard. And then, of course, step 2, you add dilute acid. Okay, keep in mind that the Grignard reagent will react with a nitrile to give you a methyl ketone. I mean, to give you a ketone. That depends on the type of Grignard reagent you are using. So Grignard will react with a nitrile to give you a ketone. Okay, if you follow that, give me a happy face. Okay, very good. So we are moving right along. Okay, I believe Chad Crawford has also joined us, so you are welcome. And I see here Jasmine Godin, you are also welcome. Okay, let us go to the next one. I said we will do 13, 14, and 15. Okay, so we are moving right along. Okay, now if you have not read a question for us tonight and your mic is working, can you pick up the mic and read this question for us? Okay, maybe, okay, everybody has spoken so far. Okay, now, Marsha, can you go ahead and read question 13 for us?
Consider 2-cyclohexanone. The gamma hydrogen is acidic. Briefly explain with the aid of resonance structures.
Okay, thank you. Okay, this should be a fairly simple question for all of you. Okay, of course, you need to know the structure of 2-cyclohexanone. So another way of testing your knowledge of nomenclature. So what we have here, 2-cyclohexanone is this here. It's a ketone, okay, and then you have a carbon-carbon double bond in the 2 position. That is why they have 2 here, okay. Okay, now if you take a look at this molecule, this here, relative to the carbonyl, this is alpha carbon. This is beta carbon, using the Greek symbol, and this here is the gamma carbon, okay? Okay, if you do the same thing here, this is alpha, this is beta, this is still the same gamma carbon. So what they are asking us here, they say this here, the hydrogen here on this gamma carbon are acidic. In other words, the pKa value less than 25 at 25. So when we say an organic proton is acidic, we are essentially saying that the pKa value is 25 or below. Okay, and now they say, how do we explain that? Okay, does anybody have an idea how to do this? But before you attack this problem, whenever you have a problem like this, to explain why a proton, an hydrogen is acidic, what you need to consider is the conjugate base, okay? You start solving the problem by taking a look at the conjugate base, okay? So you do not look at the acid itself. What you need to look at is the conjugate base before you could approach that question, which is to say that what you want to do is to remove one of these hydrogen here, in this case, since you have two hydrogen on the gamma carbon, and then you form a conjugate base. To form that conjugate base, okay? So this is your acid. This is the conjugate base. So anytime you need to explain acidity, you need to take a look at the conjugate base in order for you to do that. Now, how do we now explain this? Why is this hydrogen here, why is it considered acidic? Okay? Why would this be acidic? This here. Does anybody know how do we solve this? What do we need to use, what do we need in order for us to explain this? The acidity of this hydrogen here. Keeping in mind that it is not alpha. Resonance, excellent. We need to use resonance. In other words, what we need to do here is to explain that as a result of resonance, this conjugate base is stabilized. Okay, there is going to be electron delocalization. Electron delocalization by resonance, as a result of resonance, okay? So that is what you want to be able to do here in this particular instance. So therefore, if you can draw resonance structure for this conjugate base that also involves the rest of this molecule here, then you say, yes, this molecule is stable, the conjugate base is stable, and that is why it is acidic. Okay, so let us draw the resonance structure. Okay, we could move. In this particular instance, okay, this pair of electrons here at this point is in a p orbital, because this carbon now becomes an sp2 hybridized carbon. This carbon is sp2 hybridized carbon. This one is sp2 hybridized carbon. This one is sp2 hybridized carbon. So what we now have, we have a string or a chain of atoms that are sp2 hybridized carbon atoms, and which means that we could delocalize this electron into their p orbitals. Okay, so what we have? So we have this. Let us do the first one. I will say, okay, supposing we simply move this electron in the p orbital here to form a pi bond between this carbon and this carbon, and in so doing, this electron here will come to this carbon here. Okay, so now we have this. Now this is now here. Okay, now we could further delocalize this electron here from this carbon to this here, because this is also an sp hybridized carbon, and oxygen is also sp2 hybridized. I'm sorry, I don't mean sp, I mean sp2 right here. So therefore, we could further delocalize this electron to here. So we move this to here, which means that we move this pi electron to oxygen. And then what do we now have? So we now have oxygen is now negatively charged. Keep in mind that we have two pairs of non-bonding electron already on oxygen here. So now we have this. Now we have this. Okay. So now we have three resonance structures. Let us call this A, B, and C. A, B, and C are resonance structures of the same conjugate base. So therefore, the answer to this question is, the reason why this hydrogen is acidic is because the conjugate base that you obtain is resonance stabilized, and then you draw this structure to show that. Okay, the explanation is just that simple. The resonance stabilized conjugate base. Okay. Okay, is there any question on this? Can be stable? Yes. Okay, that is correct. That is correct. Okay, any question on this? Okay, no question. Let us move on. Okay. Victoria, can you go ahead and read this question first?
The reaction of an amine with methyl benzoate gave N-methylbenzamide. Provide a mechanism for the reaction.
Okay, thank you. Okay, so in this case, we have, they said the reaction of an amine. Notice they did not give you the amine, they just say an amine reacted with methyl benzoate to give N-methylbenzamide. Okay, so there's a little bit of trick there. Okay, so we know we have, this is methyl benzoate. It is an ester, methyl benzoate, which is the ester of benzoic acid. Okay, now we say that they say that the amine, whatever that amine is, gave this here N-methylbenzamide. N-methyl, in other words, methyl is attached to this nitrogen here. So this is N-methylbenzamide. Okay? So therefore, they now say provide a mechanism for this reaction. Now, what this is telling you, if this is the product you are going to form, since they just told you an amine, okay, as a result of the product they have given you here, now they've also given you what the amine is. The amine must be this here. Because of this product. So keep this in mind. If you, in this case, if you got this in an exam and you simply just use any amine that you feel like using, you will be wrong, because you have to use the amine that corresponds to the amine in the product. Okay. Okay. So that is the key to this particular question. Okay. Now they say provide a reaction mechanism. Okay. We should be able to do this. Okay, this will be an example of nucleophilic acyl substitution reaction. Okay, that is what that is. In other words, what are we done here? We are going to substitute this here. Okay, in other words, replace this with this. Okay. Okay, so now let us see, can we draw the reaction mechanism. Let us do this together, okay? Let me erase this so I have give myself some space. Keeping in mind this is where we want to go. Put this here. Keep in mind we want to go from here to here. To here. Okay, let me save myself some some space. Let's take this off. Okay, that way the file will not be too big, taking off my video. Okay, so now let us go ahead and do the provide the mechanism. Okay, so we know that we've already told you what type of amine that we need to use, which is this here. You know that amine, this is a primary amine. Amine have the nitrogen of the amine has a pair of non-bonding electrons. Okay, so what is the first thing we need to do here? Okay, what is the first thing we need to do? Anybody has an idea? What is the first thing we need to do? We have a carbonyl. This will be acting as a nucleophile. Okay, attack. Okay, very good. The nucleophile will attack the carbonyl. Excellent. Keep in mind you need to show this arrow, and this arrow simply means that this pair of electrons is moving here to form a bond, and this nitrogen is going to form a bond with this carbon. So we are going to move this to oxygen. You don't want too many bonds on that carbon. Okay, of course this oxygen has non-bonding pair of electrons. Okay, so now we form this intermediate. Now this is a classic example of a nucleophilic acyl substitution reaction, and all of those carboxylic acid derivative, they will undergo similar reaction. Okay, so now we have this here. Okay, so what will be the next thing that happens now? What is the next thing that happens? What is the next thing that happens? We form this tetrahedral intermediate. Tetrahedral intermediate. Okay, hydrogen shift to methoxy group. Okay. Okay, well, you could do that. You could do that. Okay. I was going to do something else, but that is also a possibility, yes. If you get an intramolecular acid-base reaction, in this case, hydrogen transfer, a proton transfer. Okay. Like I said, I was going to do something slightly different, but yes, you could see get there. In other words, this will now be the arrow will be coming here. You say we are going to pick this up, and this pair of electrons stay with. Okay, now what do you do with this at this point? What do you do at this point? You see how your tetrahedral is intermediate. What do you do at this point? Okay, anybody has an idea? Keep in mind this is where we want to come, right here. Okay, reform carbonyl. Excellent, excellent. That is what I was going to do right here. You could do that right here. Okay, reform carbonyl. So yes, we could do that now. We are going to reform the carbonyl. Okay, very good. We reform the carbonyl. If we do that, this goes away. And then what do we get? We get this. You just keep track of all of your electrons. So now we have this here. Keep in mind the hydrogen is still here. So now this is still positive. This is now positively charged. And now our main group is here. And then the methoxide is here, somewhere floating around. Okay, since we are losing the methoxide here. So now what happens at this point? Okay, what happens at this point? Takes takes hydrogen from, okay, very good. We now come here, this methoxide is very basic. Come here, simply grab this proton here, thereby releasing electron to oxygen, and so you get to your final product. Change the color of my pen here. And so now you have this. Okay, now we have this here, and now you have this. Okay, and that is the mechanism for this reaction. And as I told you before, this is a classic, okay, nucleophilic, acyl substitution reaction, and all of those carboxylic acid derivatives, they undergo this similar type of reaction. You have a nucleophile, and the nucleophile could replace any of the group that is attached to the carbonyl group. Okay. Okay. So now I think we only have one more question. And it's 9:04. We have spent about 1 hour. Let us do the last question, and then we call it a day. Okay, let us see. Frederick, can you go ahead and read this question first? Question 15.
Starting with acetoacetic acid, ester, provide a mechanism for the synthesis of 2-butanone.
Okay, thank you. Okay, so in this case, we have acetoacetic ester or ethyl acetoacetate. Ethyl acetoacetate. Okay, which is this molecule here, of course. Okay, that's an ethyl group. And now they want you to go using this here to go to make 2-butanone. Make 2-butanone. This should be fairly simple, but they want you to give the mechanism for this. Okay, so in other words, this is the acetoacetic ester synthesis. They simply want you to give the mechanism of the acetoacetic ester synthesis. Okay, so they want you to give the mechanism. Okay, so let us start. Let us start one step at a time. So I need you guys to help me out here. We start with the acetoacetic ester. Okay, in the first step, what is going to happen here, since they are asking us to give the mechanism, let us show how this actually happens. We want to show the hydrogen is here. Okay. What is the first thing that we're going to do here? Okay, okay. What is the first thing that we're going to do here? Keep in mind they want us to draw the reaction mechanism for the acetoacetic ester. Okay? Okay, we use ethoxide. Very good. So the ethoxide comes in here. Of course, we would now come in to grab this here. And this pair of electrons comes here. So now we have this. So we form the enolate. Now what do we now do here? Keep in mind this is where we want to go. By the way, let us do a little bit of analysis here. If you look at this, okay, we're going to have to make an assumption that this carbonyl here of this product is this here, right? So if we make that assumption, then we also have to make another assumption that this here, this carbon here will be this carbon. So what does that tell us? Okay, what kind of alkylating agent do we need to use? Because if you look at here, we need to form a new carbon-carbon bond right here. So what is the alkylating agent we are going to use here? Okay, methyl bromide. Excellent. Okay, very good. So now we have to use methyl bromide. Okay. And we know this is an SN2 reaction. And what does that mean? Simply means that the nucleophile comes here, attacks this from the back, and then the bromine leaves. Okay, so now we form, let us use a different color here. I use green. Okay, so now we form this. Okay, now we have this here. Okay, now what is the next we need to do now? Keep in mind we have to give the mechanism. What is the next thing we need to do? We have alkylated the acetoacetic ester. Okay, exactly. Now we have to give the mechanism for the hydrolysis. Okay, the mechanism for the hydrolysis. Keep in mind we have this. Okay, water is here. Okay, this is acid catalyzed hydrolysis. Okay. So now we now say the water will come in, attack this. So now we are going to now go through another example of a nucleophilic acyl substitution reaction. Okay, and this goes here. Okay, if you notice here, this will be similar to the last mechanism we gave you with the benzamide in the last question. Okay, so we now have that. Okay, so this gives you here. By the way, this will now have to be a reversible process. So we now have this. Okay, and then you have this here. And now we have this water is attached to here. Okay, and this is here. So now what do we do at this point? What do we do at this point? Okay, what do we want to do at this point? Okay, we form this tetrahedral intermediate. So what do we do? What is going to happen next? Any idea? What is going to happen next? We have this here. We need to get to here, finally. Okay, so we need to reform. Okay, epoxide takes epoxide take hydrogen. Okay. Okay, so to do that, you need to reform the carbonyl. So you reform the carbonyl, and this will go. Okay, so therefore, you now have this. Since we are going to reform this, and this is now here, it's a reversible process. Okay, and of course this is here, and the ethoxide, just as you guys said, ethoxide will be here to grab this here. Okay, so what do we get? The ethoxide comes here, grab this proton, and this comes here. Now we go through here again, another reversible process. If you notice here, this is the reverse of the Fischer esterification. This is the reverse of the Fischer esterification. So now we have this. And now we have this here. Now we have this here. Now we have this here. Now we have this still here. Okay, so now we've gone from the ester. What we've given you now is the mechanism for the hydrolysis of an ester to a carboxylic acid, which is the reverse of the Fischer esterification, which is going from a carboxylic acid to an ester. In this case, when you're going from an ester to carboxylic acid, you start with dilute acid. Okay. On the other hand, if you are going from a carboxylic acid to an ester, you start with concentrated acid. Okay. So now we form this. So now once you form the beta-keto carboxylic acid, since we are getting to the end of this, let me put my video. Can you guys hear me? If you can hear me, give me a happy face. Okay, good. Okay, put my video back. Now, the last step of this reaction mechanism, we're going to lose carbon dioxide. So what happens? This comes here, and this comes here. So in essence, now we are going to form this. We form enolate right here, and of course the proton is here somewhere, and then of course carbon dioxide. And then what happens, of course, the enolate will simply just grab the proton right here. Okay? And then we get our product right here. Now get the 2-butanone. Okay, so what we've given you here is the mechanism of the acetoacetic ester synthesis. This is the mechanism of the acetoacetic ester synthesis. I don't think I had a chance to give this to you in class, but now you have it. Okay? Okay, is there any question on this? I think It's about 9:16. I'm sure you guys want to go home and rest for the day. Is there any question before we go? Okay, if there is no question, we have come to the end of our session today. I want to thank all of you guys for taking time out on a Friday evening to join this session. And what I will do, I will post the video no later than at 12 o'clock tomorrow afternoon. Okay. So I will see you guys on Tuesday. If anybody wants to stay around for another 5 minutes, I will stay around for another 5 minutes. In the meantime, let me go ahead and turn off the recording, and so the session is officially over.